part D.4 Merge Operation. So this is the key operation of this sorting algorithm. All right. So to solve the problem number 15, so let us look at the description of the whole situation here. Yeah. How to achieve balanced subarrays. When we have a chance to make a decision to split our data, we try to split as even as possible. So that's simple, all right? Yeah. So the idea, whenever we merge two subarrays, we make them of equal size. So we split first, right? So the merge, all right, so here we use divide and conquer approach. Divide and conquer. So there is a divide step. At a divide step, we try to split as even as possible. Then conquer. The conquer step, we call the function recursively. So we use recursion to take care of the conquering part. Yeah. Then the last step, the combine step. The combine step, that's our merge step. So that's the topic of this video, merge operation. All right. So now let me just use this line segment to represent the whole array. Before we start, we have this whole array, unordered array. Then divide and conquer. When we divide, we split in the middle. Yeah. So the size of two subarrays as close as possible, almost even, the difference at the most one. Yeah. Depends on the number of elements, even or odd. Odd number, even number. So, yeah. Then, after we get two subarrays, the next time recursion, divide and conquer another round, split in the middle of each subarray, and so on. Okay? Split more and more. Yeah. Each subarray becomes smaller and smaller, but we have to stop splitting somewhere. We cannot split forever. Yeah. So stop splitting when each file contains just one element. So you cannot split anymore. Already one element. After that, now we need to merge. Start merging level by level. Yeah. So let's look at the merge part. Merge two adjacent subarrays. All right. So then each individual resulting subarray is sorted. Yeah. So each one after the merge sorted, right? Yeah, and so on. Then next round merge. All right, so then each merged subarray also sorted. Like this, round by round, next round sorted. Yeah. All right. The last one, when we merge the last two subarrays, we get the whole array sorted. How about this idea? First, this is a completely different idea comparing our previous, all those sorting algorithms. Different idea. Yeah. Second, the main step here is the merge step. Okay? So if we take care of the merge step, we have the whole sorted array. Yeah. All right, so here, after we get it sorted, we have one special goal in our mind. hope it can avoid poor worst case performance. Why we can hope that, right? Why we can hope this? Okay? So far, all the sorting algorithms we have learned so far, they cannot avoid worst case performance, right? They cannot avoid worst case performance. Yeah. Their worst case performance or big theta of n squared. That's not good. So we do not like this bad. We do not like this bad. Okay? Our goal, more specifically, we like our worst case efficiency n log n. N log n. That is our goal. Okay? Yeah. We hope this merge sort can give us this kind of worst case. Why we have the hope? Why we have hope like this? Reason is very simple. Because we are making even split following balancing principle. The reason we use the balancing principle, we can avoid bad worst case. That's the rationale of our method. Avoid poor worst case. All right, so okay, let's move to next step. We want to look at the main merge step, the details. All right. Let me use the diagram. We want to merge these two subarrays, each one already sorted. All right. When we do the merge, we need to use the ordered data information. All right. First comparison, we look at the first element of each subarray. Compare. When we do the comparison, there is a smaller element, there is a larger element. So min 0, the smaller one, max 0, the larger one. Right? Yeah. Then one thing, after one comparison, we get a min 0. We know this min 0 must be the smallest element of all the elements in two arrays. Okay? In other words, this min 0 must be we can put it in place because we know its location. That's the first element of our destination array. So this is our destination array. That min 0 is the smallest of all, so that is the first element in the destination array, and we put it in place. One comparison, we put one element in place. All right. The next comparison, because max 0 is left, we cannot put max 0 in place because we don't know if we should put it here or not. We don't know. Okay? Yeah. All right. The max 0 could be B0 and also could be A0. Two cases. Here we consider the first case 1, the max 0 is B0. If max 0 is the B0, that means A0 is put in place. So the next comparison should be between A1 and B0. A1, B0, the smaller one, we call it min 1. The larger one, max 1, and so on. And after this comparison, we know we can place min 1 in place. So one more comparison, we can put one more element in place, and so on. So we keep doing things like this. Every time one comparison results in one element in place. Yeah. Adding up. Yeah. Then this one, next to last one, we put this in place. After that, only one element left. The last element left. Then we do not need to do comparison. because the last element can only go this location. Last element. Okay? All right. So we just put there. Yeah. So this is our observation. For every new min added, may need one comparison. May need one. Yeah. Because sometimes we do not need. Yeah. Later you will see sometimes we can put elements in place without doing any comparison. That could happen. Yeah. So you will see may need one. Yeah. Comparison except the last one. Okay. Yeah. Except the last one. Last one we never need to do comparison. Some elements before the last one, sometimes we need to do comparison. Sometimes we may not need. Depends on the situation. You may not understand. Some of you may not get the point here, because later if you see our best case, worst case, then you will get the point. We have the best case, we have worst case. The best case, the minimum number of comparisons we need to put all elements in place. Worst case, the maximum number of comparisons we need to put all the elements in place. And there is a difference between these two cases. Yeah, so we will see that. Yeah. Here, that's what we have. Okay, so we can do comparisons in this way, and finally we get all the elements in place. That means we merge two arrays. Yeah. Next, the worst case. We want to look at the worst case. Okay, all right. Yeah. So for the worst case, look at the number of elements. The first subarray k elements. Second subarray here also k elements. Right? Yeah. Every time we need to put one element in place, we need one comparison. If this occurs repeatedly, except the last one we don't need comparison. So you can see we need this many comparison, 2k minus 1. Total number of elements of the two arrays minus the last one. Last one we don't need. Okay, so minus the last one. Yeah. 2k minus 1. So that's the worst case. Yeah. All right. But this, for the worst case, two subarrays have the equal size k. With the same method, we can get, if we consider the first subarray has n elements, the second subarray has n elements, m and n. M and n could be different. Okay? So here we want to consider the general situation, the general merge step, not necessarily equal size subarrays, the general. What is the worst case? Now, the answer also pretty straightforward, using our previous way. Yeah. Every time we put one element in place, we need one comparison, except the last one. So the answer is total number of elements minus 1. Okay, n plus n minus 1. So that is the general worst case. Okay. All right. Next, best case, the general best case. Okay. All right. The minimum number of comparisons we need to merge two sorted arrays. Okay. The first one, m elements. Second one, n elements. Okay. All right. How do we imagine the best scenario for us? We need a minimum number of comparisons. Yeah. All right. So look at this strategy we need here. All right. The strategy is try to exhaust So think about, if one element in one of the subarrays beats all the elements in the other subarray, then we exhaust all the elements in that subarray, right? So that's the exhausting meaning. One element in one subarray can beat all the elements in the other subarray, then we are done. We exhaust all elements in the other one, so the remaining elements, we do not need a comparison, we can put them in place directly. That is our observation. Okay? All right, so that's the strategy. Okay? Try to exhaust one of the two subarrays as early as possible. What do you mean as early as possible? Yeah, that is, how about the first element in one of the subarrays can beat all the elements in the other subarray? So we exhaust as early as possible, right? The first one already beats all elements in the other. Then we do not need to do comparison for the remaining elements in that subarray. So that's what I mean. We do not need a comparison. We can put all these elements in place. How about that? That's the best case scenario. Okay? Still, when we have chance to choose one of the subarray, we have freedom to choose. Do we exhaust the first subarray or we exhaust the second subarray? We have freedom to choose one of the two cases. So which one we should select? Then the next step of the strategy, exhaust the shorter array. If the sizes of two subarrays are different, then we just exhaust the shorter subarray. Okay? So with this strategy, we can get our best case efficiency. What is the formula for the best case efficiency? The answer, minimum of m and n. Minimum of m and the n. Because one element has to beat all the elements in the smaller, shorter subarray. So we need this many comparisons. Okay? So that's the best case. Best case, worst case. So we have everything we need to merge two sorted arrays. All right. Here, I just mentioned best case and the worst case. So you may wonder, how about the average case, right? How about the average case? Here, the average case could be very complicated, right? The average case could be very complicated. So usually, I may not ask you to do it. Okay? But if I ask you to do it, I may like to choose, I will not ask you to do the general m and n. I will give you, 2 here, 3 here, for example. Is it possible? Even that, it may not be very easy. So that's pretty challenging. Even that situation, it's pretty challenging. All right, so let me finish this video, D.4 right here.